Hello, in this lecture we will answer on two questions. The first question is to find out the area of this semicircle that is inscribed by a quarter circle, and the second question is to find out the size of this angle theta, to find out the size of this angle theta, that is one of three angles of the right triangle ABC. So we'll start with the first question. In the drawing we have a quarter circle, and inside this quarter circle we have a semicircle that is inscribed by this quarter circle. We know that the radius of this quarter circle is 3, and we want to find out the area of the semicircle that is inscribed by this quarter circle. So first of all, we will define the center of this semicircle as point O, and in the next step I will present to you a new rule that is actually rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So I will read rule number 1 again. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So we have this circle, and we know that the center of this circle is at this point, point O, and we also have tangent AB to this circle. Here, tangent AB, this tangent is tangent to this circle at this point. This is the point of tendency of tangent AB with this circle. We will define the point of tendency as point M. So point M is the point of tendency of tangent AB with this circle, and we have the radius OM. We define the radius OM as R. So the radius OM here, it is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, like in this drawing, then the tangent will be perpendicular to that radius. In this case, the tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO. That is to say, this angle will be equal to 90 degrees and this angle will be equal to 90 degrees according to rule number 1. Again, a tangent to a circle, that is to say tangent AB, is perpendicular to the radius OM. Which radius OM? The radius OM that is drawn to the point of tendency. Because of the fact that the radius OM it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle, then the tangent AB will be perpendicular to the radius MO. AB is perpendicular to MO, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so we can actually implement rule number 1 in our drawing. Here, point O is the center of the semicircle. Here, we will define this point as point A, this point as point B. We will define this point as point C, this point as point D. We will define this point as point H. We will define this point as point F, and we will define this point as point G. Here we will draw from the center of the semicircle, that is to say from point O, we will draw the radius of the semicircle to the point of tendency, that is point B. Here, this is the radius of the semicircle because of the fact that it starts from the center of the semicircle and then at point B, that is a point on the semicircle itself. Therefore, this is the radius of the semicircle. We will define the radius of the semicircle as R. Therefore, OB will be equal to R. And here, the radius OB of the semicircle is drawn to the point of tendency. That is to say, it is drawn to point B, that is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent AC will be perpendicular to the radius BO. So AC is perpendicular to BO, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. Likewise, we will join points O and D together by a straight line. OD is the radius of the semicircle because of the fact that it starts from the center of the semicircle and that's point D, that is a point on the semicircle itself. Therefore, OD is the radius of the semicircle, that is to say it is equal to R. So here we have the radius OD of the semicircle that is drawn to the point of tendency, that is to say it is drawn to point D, that is the point of tendency of tangent CH with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. Here the tangent CH will be perpendicular to the radius DO. CH is perpendicular to DO. That is to say, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. And we also know that because of the fact that this is a quarter circle, CAH is a quarter circle, point C must be the center of this quarter circle and angle ACH must be equal to 90 degrees because of the fact that ACH is a quarter circle. Therefore, angle ACH must be equal to 90 degrees and point C must be equal to the center of this quarter circle. So actually, in quadrilateral BOCD, we have 3 right angles and the sum of 3 right angles is 90 times 3 is 270 degrees. I will repeat again. In quadrilateral BOCD, we have 3 right angles. The sum of 3 right angles is 90 times 3, that is 270 degrees, plus the size of the fourth angle, this angle that is actually angle BOD. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we will subtract 270 degrees from this equation, and we will get that the missing angle BOD, will be equal to 360 degrees minus 270 degrees. It is equal to 90 degrees. So the missing angle is the right angle, it is equal to 90 degrees. So here, this angle equals to 90 degrees. So we actually found out that in quadrilateral BOCD, this quadrilateral, we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral BOCD as a rectangle. Quadrilateral BOCD is a rectangle. And we also have rule number 2. According to rule number 2, the opposite sides of a rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. That is to say, according to rule number 2, this rule, the opposite sides of rectangle BOCD are equal to each other. It means that side BO must be equal to side CD. BO equals to CD according to rule number 2, that the opposite sides of a rectangle are equal to each other. But we know that BO is the radius of the semicircle, that is to say it equals to R. So we can write here that BO equals to R, and from this equation R equals to BO equals to CD, we will derive that CD is also equals to R. Okay, CD is also equals to R. Here CD equals to R. Likewise, according to rule number 2, OD must be equal to BC. Side OD must be equal to side BC in rectangle OBCD. Side OD must be equal to side BC in rectangle OBCD. But here we know that OD equals to R. OD equals to R, so from this equation, here OD equals to BC according to rule number 2, that the opposite sides of a rectangle are equal to each other. So from this equation, R equals to OD equals to BC, we will derive that BC is also equals to R. BC is also equals to R. So actually we found out that all the sides of quadrilateral BOCD are equal to each other, and also quadrilateral BOCD has 4 right angles. Therefore, quadrilateral BOCD, it is not a rectangle but a square. So we will write here that quadrilateral BOCD is a square. Okay? In the next step, we will join points O and C together by a straight line. Line segment CO or OC, it is the diagonal of square BOCD. We will find out the length of diagonal CO by implementing the Pythagoras theorem on the green right triangle, triangle ODC. Okay? We will implement the Pythagoras theorem on the green right triangle, triangle OCD. So in the right triangle, triangle OCD, the right green triangle, triangle OCD, according to the Pythagoras theorem, PT is the abbreviation for Pythagoras theorem, we will get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is CO squared. Here, CO squared will be equal to OD squared plus DC squared. Okay, so according to the Pythagoras theorem, in the green right triangle, triangle OCD, CO squared equals to OD squared plus DC squared. CO is the missing variable, so we leave it as it is. We will get that CO squared equals to OD squared. OD is R, so OD squared will be equal to R squared plus this DC squared. DC equals to R, so DC squared will be equal to R squared. So in conclusion, we found out that CO squared equals to R squared plus R squared. That is to say, CO squared equals to R squared plus R squared is 2R squared. Here we take a root out of this equation and we get that the value of CO, that is the diagonal of square BOCD, it is equal to square root of 2 times R. Okay, CO equals to square root of 2 times R. Here we can write that CO equals to square root of 2 times R. R is the radius of the semicircle. So here, in the next step, we will extend the diagonal CO of square BOCD until it touches the quarter circle at this point, and we will define the touching point of the extended CO of the extended diagonal CO and the quarter circle SS, and in the next step we will calculate the length of line segment OS. What is the length of line segment OS? The length of line segment OS, it is very easy to see from the drawing that the length of line segment OS will be equal to CS minus CO. CS minus CO equals to the length of the small line segment OS. So here we get that the length of the small line segment OS equals to OS. It is actually CS. Again, the length of line segment OS equals to CS. Here, CS minus CO. CS minus CO. So CS, what is the length of CS? C is the center of the quarter circle, and S is the point of the quarter circle itself. Therefore, CS is the radius of the quarter circle, because any line segment that starts from the center of the quarter circle and ends at the point of the quarter circle itself, it is defined as a radius. And we know that the radius of the quarter circle equals to 3 units. So CS equals to 3 units. And we already found out that CO, the diagonal of the square, equals to square root of 2 times R. So in conclusion, we found out that the length of line segment OS equals to 3 minus square root of 2R. This is equal to 3 minus square root of 2R. Okay? In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and we will extend the diagonal OC by a straight line until it touches the circle. Okay? Here, the touching point of the extended diagonal OC with the circle will be defined as point M. Again, point M is the touching point of the extended diagonal OC with the circle, so it is equal to, it is point M. So what is the length of line segment MC? C is the center of the quarter circle, and M is the point of the circle itself. And this is exactly the definition of a radius. That is to say, MC is the radius of the quarter circle and the radius of the circle itself. That is to say, it is equal to 3 units. In the next step, I will present to you a new rule that is related to the two diagonals that intersect with each other inside the circle. So here, this will be rule number 3. According to rule number 3, if two diagonals intersect with each other inside this circle, this is diagonal AB. If two chords intersect with each other inside the circle, this is chord AB. And this is called CD. You can see in the drawing that chord AB intersects with chord C at this point. This is the intersection point between the two chords. We will define the intersection point as point O. So if we have two diagonals that in two chords, like here in this drawing, two chords that intersect with each other inside a circle, then the following relationship exists between their sides, between the sides of the chords. The following relationship exists between their parts, between the parts of the chords. Here, CO times OD, CO times OD equals to AO times OB. I'll repeat again. If two chords intersect with each other inside the circle and the intersection point is point O, then CO times OD will be equal to AO times OB. So we actually can implement rule number 3 in our drawing. In our drawing, we have chord MS that intersects with chord GF at point O. Point O is the intersection point. So I'll write it down. In our drawing, chord MS intersects with chord GF at point O. Point O is the intersection point between the two chords. I'll repeat again. Chord MS intersects with chord GF at point O. Point O is the intersection point. Here, what is the length of line segment GO? O is the center of the semicircle. G is the point of the semicircle itself. Therefore, GO is the radius of the semicircle, that is to say it is equal to R. Likewise, here O is the center of the semicircle, F is a point on the semicircle itself. Therefore, OF will be equal also to the radius of the semicircle, that is to say it will be equal to R. So here we will implement rule number 3 in our drawing. According to rule number 3, we will get that MO times OS must be equal to GO times OF. Okay? I repeat again, according to rule number 3 in our drawing, MO times OS must be equal to, here it is, MO times OS must be equal to GO times OF. Here MO equals to MC plus CO. MO equals to MC plus CO. And we have already found out that OS equals to 3 minus square root of 2R. OS equals to 3 minus square root of 2R. And it is equal to GO, that is R, times OF, that is also R. So in conclusion, we found out that MC plus CO times 3 minus square root of 2R will be equal to R times R, that is R squared. Here MC equals to 3 units. CO equals to square root of 2R. So in conclusion, MO equals to 3 plus square root of 2R times 3 minus square root of 2R must be equal to R squared. So the expression 3 plus square root of 2R times 3 minus square root of 2R, it is very similar to the algebraic identity that A plus B times A minus B equals to A squared plus B squared. In our specific expression, A equals to 3, A equals to 3, and B equals to square root of 2R. And this expression must be equal to A squared minus B squared. A squared minus B squared. A is 3, so A squared is 3 squared, that is 9, minus B squared. B is square root of 2R. So B squared will be equal to square root of 2R squared. Square root of 2 squared is 2. And R squared is R squared. So in conclusion, we found out that the value of this expression 3 plus square root of 2R times 3 minus square root of 2R, it is equals to 9 minus 2R squared, and this must be equal to R squared. So here we will add 2R squared to this equation, and we will get that nine equals to 2R squared plus R squared is 3R squared. So 9 equals to 3R squared. We'll divide this equation by 3. And we'll get that R squared equals to 9 over 3, that is 3. So here R squared equals to 3. We found out that R squared equals to 3. And what is the area of the semicircle? The area of the semicircle is equal to the area of the circle over 2. And the area of any circle is pi r squared. Therefore, the area of the semicircle will be equal to pi r squared over 2. Okay, so the area of our semicircle will be equal to pi r squared over 2. We have already found out that r squared equals to 3. So here we will have pi, and r squared is 3, so we will substitute r squared by 3, and then we will divide it by 2. So So in conclusion, we found out that the area of the semicircle equals to 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay, so I'll repeat again. We found out that the area of the semicircle, the area of this semicircle that is described by the quarter circle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this semicircle according to the second method. Okay, so here we define the center of the semicircle as point O, and we will use the things that we have already found out in the first method. In the first method, we actually found out that square OB CD, this square, this is actually a square. Quadrilateral BOCD is a square, and the diagonal of this square, that is CO, is equal to square root of 2R, and we already found out this is point G, this is point F, this is point H. We have already found out that GO is equal to R, that is the radius of the semicircle. OF is also equal to R, it is also the radius of the semicircle. And here, in the second method, we will join points C and F together by a straight line. So what is the length of line segment CF? We know that C is the center of the quarter circle. I will write it here that C is the center of the quarter circle, F is a point on the quarter circle itself, and this is exactly the definition of a radius. That is to say, CF is the radius of the quarter circle that is equal to 3 units. It is given as the question. Likewise, we will join points C and G together by a straight line. Here, line segment CD will be also equal to the radius of the quarter circle, that is to say, it will be equal to 3 units, for the same reasons. Why? Because point C is the center of the quarter circle and point D is the point on the quarter circle itself. Therefore, CG is the radius of the quarter circle that is equal to 3 units. So we actually created the isosceles triangle GCF. Triangle GCF is an isosceles triangle because of the fact that side GC of the triangle is equal to side CF of the triangle. Okay? Any triangles that has two sides that are equal to each other, it will be an isosceles triangle. Okay, so triangle GCF is an isosceles triangle, and the base of the isosceles triangle GCF is GF. Okay, and here CO, line segment CO, is the median to the base GF. Why CO is the median to the base? Because of the fact that CO bisects the base GF into two equal parts. That is to say, GO equals to OF equals to R. Okay, so I will copy the right triangle GCF in a new page, and we will analyze the triangle. Okay, we have the triangle, the isosceles triangle CGF. So I copied the isosceles triangle CFG in this new page. Here we know that the median to the base is CO, that is actually equals to square root of 2R. The base of the isosceles triangle CFG is FG, as you can see here. So triangle CFG is an isosceles triangle. And as you can see, the median CO to the median CO to the base FG bisects the base FG because of the fact that FO equals to OG equals to R. But we have also rule number 4 that is related to the median to the base of an isosceles triangle. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. I will read rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So here, according to rule number 4, we will implement it on our isosceles triangle, triangle CFG. According to rule number 4, the median CO to the base FG is perpendicular to the base FG. That is to say, CF is perpendicular to FG. Again, CO, the median CO to the base FG in the isosceles triangle FCG is perpendicular to the base FG. So CO is perpendicular to FG according to rule number 4. Again, CO is perpendicular to FG. That is to say, according to rule number 4, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. I'll repeat again. The median CO to the base FG is perpendicular to the base FG. CO is perpendicular to FG, that is to say, this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 4. Okay, so we can, if we can implement the rule in our original drawing, rule number 4, according to rule number 4, the median CO to the base CG is perpendicular to the base actually the median CO to the base FC, the median CO to the base FG, again the median CO to the base FG is perpendicular to the base FG. So CO is perpendicular to FG, that is to say, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay? According to rule number 4, of course. Now we will implement the Pythagoras theorem on the right triangle, triangle COG. Okay? Here we will implement the Pythagoras theorem on this right triangle, triangle COG. So I will copy the right triangle COG in a new page and we will implement the Pythagoras theorem on this right triangle, triangle COG. Okay, so here we have the right triangle, triangle COG. This is the right triangle, triangle COG that I copied from the original drawing. Okay. We will implement the Pythagoras theorem on this right triangle, triangle COG. On this right triangle, triangle COG, by PT, that is the Pythagoras theorem, we'll get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is CG, so the square of the hypotenuse is CG squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to CO squared plus OG squared. So here CG equals to 3, so CG squared is 3 squared, that is 9, and it is equal to CO squared. CO equals to square root of 2r, so CO squared will be equal to 2r squared plus OG squared. OG equals to r, so OG squared will be equal to r squared. So in conclusion, we found out that 9 equals to 2r squared plus r squared is 3r squared. We'll divide this equation by 3, and we'll get that 3r squared over 3 is r squared. R squared equals to 9 over 3, that is 3. R squared equals to 3, and the area of the semicircle, it is equal to pi r squared over 2. So it is pi and r squared is 3, so we'll substitute r squared by 3 over 2. So we found out that the area of the semicircle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 3 times 71 square units. Okay, I will repeat again. The area of this semicircle that is inscribed by the quarter circle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 3.71 square units. So we finished with the second method. In the next step, I will present to you the second question. We'll solve the second question by 2 different methods. Here we have the right triangle, triangle ABC, angle ABC equals to 90 degrees. We know that line segment OE is perpendicular to the hypotenuse AC. We also know that side BC of the right triangle, triangle ABC is equal to 6 units. Line segment OE equals to 2 units. And we also know that line segment AE equals to EC. And angle BAC equals to theta, and that is the angle that we are looking for. We want to find out the size of this angle, angle theta. In order to find out the size of this angle theta, first of all, we will do a construction. From point E, we will draw perpendicular on BC. Okay? From point E, we will draw perpendicular on point C. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. And we will define the touching point of the perpendicular from point E and BC as F. In the next step, we will define angle ACB, this angle is angle alpha. In the right triangle, triangle ABC, this angle equals to 90 degrees. This angle equals to theta, so this angle that we defined as alpha must be equal to 90 degrees minus theta. Why? Because the sum of the angles in any triangle is 180 degrees, and only if this angle will be equal to 90 degrees minus theta, the sum of the angles in triangle ABC will be equal to 180 degrees. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. So here we actually found out that alpha equals to 90 degrees minus theta. Here we will add to this equation theta and we will subtract alpha, and we will get that angle theta equals to 90 degrees minus alpha. And in the right triangle FEC, this angle equals to 90 degrees. This angle equals to alpha. So this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle to 180 degrees. And what is the size of angle DFE? The size of this angle DFE. Angle DFE is equal to this angle DFE equals to angle DFC, the big angle DEC, minus angle FEC. So the big angle DEC minus angle FEC will be equal to this angle DEC. It is very easy to see that angle DEC minus angle FEC will be equal exactly to angle FEC. Okay? So angle DFE is equal to angle DEC. According to what is given us in the question, angle DEC equals to 90 degrees. So we'll substitute angle DEC by 90 degrees. And we have already found out that angle FEC equals to 90 degrees minus alpha. So we'll substitute angle FEC by 90 degrees minus alpha. We'll open the brackets here and we'll get that angle DFE, the angle that we are looking for, it is equals to 90 degrees. Minus 90 degrees is 0. Minus and minus is plus, so it is plus alpha. So in conclusion, we found out that the missing angle DFE equals to alpha. Okay, this angle equals to alpha. So if this angle equals to alpha in the right triangle DEF, this angle equals to 90 degrees. So this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in this right triangle to 180 degrees. So this angle EDF equals to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha is equal to angle theta, we will substitute here the angle that is 90 degrees minus alpha by theta. Okay? In the next step, here we will define side DF as x, we will define side EF as y, we will define line segment AE as A. If AE equals to A, then EC will be also equal to A because AE equals to EC. In the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, this right small triangle, triangle EFC. So why those two right triangles are similar to each other? First of all, those two angles, the equal to each other, they are both equal to 90 degrees. So angle ABC in triangle ABC is equal to angle EFC in triangle EFC, and both angles are equal to 90 degrees, they are right angles. I will return and repeat again. That angle ABC equals to angle EFC equals to 90 degrees. Both angles are equal to 90 degrees. Okay? In addition, here actually 90 degrees minus alpha equals to theta. So we can write here that 90 degrees minus alpha equals to theta. So actually those two angles, they are equal to each other. They are both equal to theta. Okay, so we can write down that angle BAC of triangle ABC is equal to angle FEC of triangle EFC, and both those two angles are equal to theta. Finally, this angle alpha is a common angle, it belongs to both triangles. You can see that angle BCA belongs to triangle ABC, and this angle alpha also belongs to the small right triangle FCE. So we can write down that angle BCA is equal to angle FCE and it is actually equals to alpha. It is actually a common angle that belongs to both triangles. Actually, we wrote here that the angle equals to itself. The angle equals to itself, and we presented this angle in two different names in order to emphasize that it belongs also to the right triangle ABC, and it also belongs to the right triangle FEC. So we actually proved that all the angles of triangle ABC can point to all the angles of triangle EFC. Those two angles, they are both equal to alpha, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. And this angle is a common angle that belongs to both triangles. So this angle equals to itself. Therefore, we prove that the right triangle ABC is similar to triangle EFC according to angle similarity rule. So I will write it down. We proved that the right big triangle ABC, is similar, this is the sign of similar, to the right big triangle EFC according to angle similarity rule. And from the fact that triangle ABC is similar to triangle EFC, we will conclude hence that AB over AC in triangle ABC is equal to EF over EC in triangle EFC. I repeat again. From the fact that triangle ABC is similar to triangle EFC, we'll conclude that AB over AC in triangle ABC is equal to EF over EC in triangle EFC. So actually, AB, according to equation number 1, AB over AC equals to A plus A, that is 2A. So we'll substitute AC by 2A, and it is equal to EF. It is equal to EF. EF is Y according to our definition. So we'll substitute EF by Y over EC. EC equals to A, so we'll substitute EC by A. So in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. Here we have A on both sides of equation number 1, so A will get cancelled, and we left only with AB over 2 that is equal to Y. Here we will multiply this equation number 1 by 2, and we will get that according to equation number 1, AB equals to 2Y. AB equals to 2Y, so we can write down here that AB equals to 2Y. In the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle DEF. So why those two triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to 90 degrees. So angle ABC of triangle ABC is equal to angle EFC of triangle EFC. It is actually angle DFC, angle EFD of triangle EFD, and both angles are equal to 90 degrees. I repeat again, angle ABC is equal to angle EFD, and both angles are equal to 90 degrees. In addition, those two angles, they are equal to each other, they are both equal to theta. So angle BAC of triangle ABC is equal to this angle, angle EDF, and both angles are equal to theta. I'll repeat again. Angle BAC equals to angle EDF, and both angles are equal to theta. And finally, those two angles are equal to each other, they are both equal to alpha. So angle DEF, or angle here, angle BCA of triangle ABC, is equal to this angle, angle DEF, and both angles are equal to alpha. I'll repeat again, angle BCA equals to angle DEF, and both angles are equal to alpha, so we prove that all the angles of triangle ABC are equal congruently to all the angles of triangle ABC are correspondingly equal to all the angles of this triangle, triangle EDF. Why? Because both those two angles are equal to alpha. Both those two angles are equal to theta, and both those two angles are equal to 90 degrees. So, therefore, we can derive from it that the right triangle ABC is similar to the right triangle EDF according to angle similarity rule. So I write it down. We'll conclude that the right triangle ABC is similar to the right triangle EDF, and they are similar to each other according to angle similarity rule. Okay? And from the fact that those two right triangles are similar to each other, we will conclude, hence, we derive from it that AB over BC in the right triangle ABC is equal to DF over FE. I'll repeat again. We'll conclude from the fact that triangle ABC is similar to triangle DEF, that AB over BC equals to DF over FE. AB equals to 2y, so we'll substitute AB by 2y. BC equals to 6 units according to what is given as the question, so we'll substitute BC by 6. DF equals to x according to our definition, FE equals to y according to our definition. So in conclusion, we found out that according to equation number 2, 2y over 6 equals to x over y. Here we will divide both the numerator and the denominator of this side of equation number 2 by 2. And we will get that according to equation number 2 here, 2y over 2 is y, and 6 over 2 is 3, and this is equal to x over y. Here we will cross multiply this equation number 2, and we will get that according to equation number 2, y squared, it is equal to 3x. According to equation number 2, we found out that y squared equals to 3x. But if we focus on the right triangle DEF, in the right triangle DEF, according to the Pythagoras theorem, it is very easy to see that according to the Pythagoras theorem, in the right triangle DEF, x squared plus y squared equals to 2 squared. X squared plus y squared equals to 2 squared, that is 4. So we actually found out that according to equation number 3, in the right triangle DEF, x squared plus y squared equals to 4. So here we can substitute y squared in this equation number 3, by 3x from equation number 2. Okay, we'll do it now, and we will get that according to equation number 3, x squared plus y squared, this is 3x, is equal to 4. Okay, we found out that according to equation number 3, x squared plus 3x equals to 4. Here we will subtract 4 from this equation, and we will get the quadratic equation that x squared plus 3x minus 4 equals to 0. Actually, the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. in this general formula for a quadratic equation, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X will be equal to minus b plus minus square root of b squared minus 4 times ac over 2a. Okay, in our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we will put the data inside the formula for x, and we will find out the value or the values of x. So here we will get that x equals to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared will be equal to 3 squared, that is 9, minus 4 times a is 1, times c is minus 4, over 2a. A is 1, so 2 times 1 is 2. In conclusion, we found out that x equals to minus 3 plus minus, and here we have minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So inside the root we have only 25 over 2. So here we have x equals to minus 3 plus minus the square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we actually found out that x1 equals to minus 4, but because of the fact that x is the length of side df of the right triangle in df, x must be a positive number. X is the length, therefore it must be a positive number. Therefore, x can never be equal to minus 4. That is a negative number, so we will cancel the solution, and we left only with the second solution for x, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x2 equals to 1. Here x equals to 1, so I will copy the right triangle EDF, and we will find out the value of cosine theta. Here x equals to 1. Okay? So this is the right triangle EDF, this is angle theta. So here cosine theta in the right triangle EDF, the right triangle EDF, cosine theta equals to df over de. Here df is equal to x, that is equal to 1. de equals to 2 according to what is given as the question. So in conclusion we found out that cosine theta equals to 1 over 2, and if cosine theta equals to 1 over 2, it means that theta itself will be equal to 60 degrees. So the answer to the question is the size of angle theta is equal to 60 degrees. Okay, the size of this angle theta, it is equal to 60 degrees. We finished with the first method. In the next step, I will present to you how to find out the size of this angle theta according to the second method. Okay? First of all, we will define angle ACB as alpha, and we know that this angle equals to theta. This is actually a right angle that is equal to 90 degrees. Angle ABC equals to 90 degrees. This angle equals to theta in the right angle ABC. This angle equals to 90 degrees. So this angle must be equal to 90 degrees minus theta. So in conclusion, we have the equation that alpha equals to 90 degrees minus theta. In the next step, we will focus on the right angle ABC, and we will find out the cosine alpha, the value of cosine alpha in the right angle ABC. So I will copy the right angle ABC in a new page, and we will find out the value of cosine alpha in the right angle ABC. Okay? So this is the right triangle ABC. But here we will, as we did in the first method, A equals to A and EC equals to AE, so EC will be also equal to A. Actually, the hypotenuse AC, according to our definition, it is equals to A plus A, that is to say, it is equals to 2A. So here, this is the right triangle ABC that I copied from the original drawing. So in the right triangle ABC, you know that cosine alpha equals to BC over AC. So cosine alpha equals to BC, that is 6 units according to what is given as the question, over AC, that is 2A according to our definition. So in conclusion, we found out that cosine alpha equals to 6 over 2A. Here we divide both the numerator and the denominator on this side of the equation by 2. 6 over 2 is 3 and 2 over 2 is 1, so it is A. In conclusion, we found out that cosine alpha, according to equation number 1, is equal to 3 over A. Here we will multiply this equation number 1 by A, and then we will divide it by cosine alpha, and we will get that according to equation number 1, A equals to 3 over cosine alpha. Okay, A equals to 3 over cosine alpha. In the next step, we will focus on the right triangle CED. I will copy the right triangle CED in the new page, and we will analyze the right triangle CED. So this is the right triangle EDC that I copied from the original drawing. In the right triangle, triangle EDC, this will be equation number 2. Tangent alpha is equal to DE over EC. That is to say, according to equation number 2, tangent alpha equals to DE, that is 2, according to what is given as the question, over EC, according to our definition, EC equals to A. So in conclusion, we found out that tangent alpha equals to 2 over A, but according to equation number 1, we have already found out that A is equal to 3 over cosine alpha. So we can substitute A in equation number 1. We can substitute A in equation number 2 by 3 over cosine alpha from equation number 1. We'll do it now and we'll get that according to equation number 2, tangent alpha equals to 2 over A, but A, according to equation number 1, equals to 3 over cosine alpha. So we'll substitute A from equation number 2 by 3 over cosine alpha from equation number 1. Very simple. And we'll get that according to equation number 2, tangent alpha equals to 2 times cosine alpha over 3. We know that tangent alpha is equal to sinus alpha over cosine alpha, so we'll substitute tangent alpha in this equation, equation number 2, by sinus alpha over cosine alpha. We'll do it now and we'll get that tangent alpha equals to sinus alpha over cosine alpha, and it is equals to 2 times cosine alpha over 3. Here we'll cross multiply this equation, equation number 2, and we'll get that according to equation number 2, 3 times sinus alpha equals to 2 times cosine square alpha we have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. Here we will subtract sine square alpha from this trigonometric identity, and we will get that cosine square alpha is actually equals to 1 minus sine square alpha. So that is to say, we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha from the trigonometric identity. We will do it now and we will get that according to equation number 2, 3 times sine alpha equals to 2 times cosine square alpha, and the cosine square alpha according to this trigonometric identity equals to 1 minus sine square alpha. So here we will open the brackets on this equation, equation number 2, and we'll get that according to equation number 2, three times sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. Here we will add 2 sine minus 2 times, we will add 2 sine square alpha to this equation, and we will get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. Here we will subtract 2 from this equation, equation number 2, and we will get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have quadratic equation. The coefficient A equals to 1, and the coefficient A equals to 2, of course, here, as you can see. The coefficient B equals to 3, and the coefficient C equals to minus 2. And the variable that we are looking for is sinus alpha, so x equals to sinus alpha. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. We have the coefficients of our specific quadratic equation, and the variable that we are looking for is sinus alpha, so we will put the data inside the formula for x, and we will find out the value of the values of sine alpha, because x equals to sine alpha. So we will get, according to this formula, that x that is equal to sinus alpha is equals to minus b. B equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 2, and c is minus 2, over 2a. 2 times a is 2, so 2 times 2 is 4. So here we got that sinus alpha equals to minus 3 plus minus. Here we have minus 4 times 2 is minus 8. Minus 8 times minus 2 is plus 16. 16 plus 9 is 25. So inside the root we have only 25. That is what is left, over 4. So here we have sinus alpha equals to minus 3 plus minus, the square root of 25 is 5 over 4. So here we will have two solutions that are possible for sinus alpha. The first solution for sinus alpha will be minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So we actually found out that the first solution for sinus alpha is minus 2, that is to say sinus alpha equals to minus 2. But because of the fact that the function alpha can accept values that are ranging from minus 1 to plus 1, here sinus alpha can receive values that are greater than equal to minus 1 and are smaller or equal to 1. And minus 2 exceeds this range of values that sinus alpha can accept. Therefore, it is incorrect solution, that is to say sinus alpha can never be equal to minus 2. Therefore, this solution is incorrect solution. So we will focus on the second solution. The second solution for sinus alpha is the sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. So we know that sinus alpha equals to 1 over 2. So here, if sinus alpha equals to 1 over 2, it means that alpha itself will be equal to 30 degrees. And we have already found out that alpha equals to 90 degrees minus theta. Alpha equals to 90 degrees minus theta. We found out that alpha equals to 30 degrees, so we'll substitute alpha by 30 degrees, and we get that 30 degrees equals to 90 degrees minus theta. Here we will add theta to this equation, and we'll subtract 30 degrees, and we'll get that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees. So we found out that angle theta, the angle that we are looking for, it is equals to 60 degrees according to the second method also. So here angle theta equals to 60 degrees. We finished with the second method. In the next step, I will summarize the lecture. Okay? We'll start with the first question, of course. In this question, we have a semicircle that is inscribed by a quarter circle. We know that the radius of the quarter circle is equal to 3 units. And we want to find out the area of the semicircle that is inscribed by the quarter circle. So we define the center of the semicircle as point O. And then I presented to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we have tangent AB, tangent AB is tangent to this circle at point M. Point M is the point of tangency of tangent AB with this circle. The center of this circle is at point O. So if from point O we will draw the radius to the point of tangency, here OM, the radius OM, it is drawn to the point of tangency. That is to say, the radius OM, it is drawn to point M, that is the point of tangency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to that radius. That is to say, in this case, tangent AB will be perpendicular to the radius MO. It means that this angle equals to 90 degrees, and this angle must be also equal to 90 degrees. So whenever you have a radius that is drawn to the point of tangency, then the tangent will be perpendicular to that radius. In this case, tangent AB will be perpendicular to the radius MO. That is to say, this angle equal to 90 degrees, and this angle will be also equal to 90 degrees. Okay? We implemented rule number 1 in our drawing. Here, from point O, we drew the radius to the point of tendency, that is to say to point B, that is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, tangent AC will be perpendicular to the radius BO. AC is perpendicular to BO, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. Likewise, from point O we drew the radius to the semicircle that is drawn to the point of tendency, that is to say the radius OD, it is drawn to point D, that is the point of tendency of tangent CH with this semicircle, and whenever you have the radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say the tangent CH will be perpendicular to the radius DO. So CH is perpendicular to DO, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. Okay, and here, because of the fact that AC edge is a quarter circle, point C must be the center of the quarter circle, and angle AC edge must be equal to 90 degrees. So in quadrilateral OBCD we have 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees. So the sum of those 3 right angles plus the size of the 4th angle, that is actually angle BOD, in total they must be equal to 360 degrees. I will repeat again, the sum of 3 right angles, that is 270 degrees, plus the size of the 4th angle, that is actually angle BOD, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we subtracted 270 degrees from this equation, and we found out that the missing angle, angle BOD, is equal to 360 degrees minus 270 degrees, it is 90 degrees. So this angle, angle BOD, equals to 90 degrees. Therefore, actually in quadrilateral BOCD we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So in quadrilateral BOCD, we can relate to quadrilateral BOCD as a rectangle. Okay, so quadrilateral BOCD is a rectangle because it has 4 right angles. And we have also rule number 2, that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle BOCD must be equal to each other. That is to say, BO must be equal to CD according to rule number 2. BO must be equal to CD according to rule number 2, that the opposite sides of a rectangle are equal to each other. Here we know that BO equals to R. So we can write here that BO equals to R. And from this equation, R equals to BO equals to CD, we will derive that CD is also equals to R. Okay, here we can write down that CD is equal to R. Likewise, according to rule number 2, we will get that OD must be equal to BC. According to rule number 2, OD must be equal to BC. But we know that OD equals to R, it is the radius of the semicircle. So here OD equals to R, and from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. Here BC is also equals to R, so we found out that in quadrilateral BOCD, all of its sides are equal to each other, they are equal to R, and it has also 4 right angles, therefore quadrilateral BOCD is not a rectangle but a square. Okay, so quadrilateral BOCD is a square. Then we join point C and O together by a straight line. CO is the diagonal of square BOCD. Okay, CO is the diagonal of square BOCD. And in order to find out the length of the diagonal CO, we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CD squared equals to CO squared, the square of the hypotenuse, it is CO squared equals to CD squared plus DO squared. Okay, in the right triangle OCD, according to the Pythagoras theorem, CO squared plus OD squared equals CO squared equals to OD squared plus DC squared. So CO squared equals to OD equals to R, so OD squared is R squared. Here OD squared is R squared. And DC equals to R, so DC squared will be equal to R squared. Here DC squared equals to R squared, so in conclusion we found out that CO squared equals to R squared plus R squared. R squared plus R squared is 2R squared. So in conclusion we found out that CO squared equals to 2R squared. We took a root out of this equation and we found out that CO equals to the square root of 2 times R. So here the length of diagonal CO square BOCD, it is equals to 2R, to square root of 2 times R, that is the radius. R is the radius of the semicircle. Okay? Then we extend that diagonal CO by a straight line until it touches the quarter circle at this point, point S, and we found out the size of the length of line segment SO. The length of line segment SO, it is very easy to see from the drawing that SO equals to SC minus OC. Again, SC minus OC equals exactly to SO. Okay, again, OS equals to SC minus CO. And here, so OS, the small line segment OS, equals to S, it is actually, again, line segment SO equals to SC minus OC. Okay, the small line segment OS equals to SC minus OC. SC minus OC. So the line segment SO will be equal to SC. SC is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle, that is to say from point C, and ends at point S, that is the point of the quarter circle itself. And this is exactly the definition of a radius. Therefore, SC is the radius of the quarter circle, that is equal to 3 units. So SC is the radius of the quarter circle, that is equal to 3 units. And CO, the diagonal of the square, we already found out that is equal to square root of 2 times R. So in conclusion, we found out that the length of the small line segment SO, it is equal to 3 minus square root of 2R. And then we extended, we actually completed the quarter circle to a circle. And then we extended diagonal OC by a straight line until it touches the circle at this point. We define the touching point of the extended diagonal OC in the circle as point M. What is the value of MC? MC is the radius of the circle and also the radius of the quarter circle. Why? Because C is the center of the circle and the center of the quarter circle, and M is the point on the circle itself, and this is exactly the definition of a radius. Therefore, MC is the radius of the quarter circle, that is equal to 3 units. Then I presented to you a new rule number 3, that is related to 2 chords that intersect with each other inside the circle. So here we have this circle, and we have 2 chords. Chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. Okay? And whenever you have 2 chords that intersect with each other inside the circle, then the following formula is true, that CO minus OD equals to AO minus OB. Okay, again, CO times OD equals to AO times OB. So we can implement rule number 4 in our, we can implement rule number 3 in our drawing, because in our drawing we have chord MS, that intersects with chord GF at point O. Point O is the intersection point of chord MS with chord GF. Therefore, according to rule number 3, we will get that MO times OS equals to GO times OF. I'll repeat again. Chord MS intersects with chord GF at point O. Therefore, according to rule number 3, MO times OS equals to GO times OF. MO, line segment MO equals to MC plus CO. Okay? MO equals to MC plus CO. We have already found out that OS equals to 3 minus square root of 2R. Here, OS equals to 3 minus square root of 2R. GO equals to R, that is the radius of the semicircle. Why? Because O is the center of the semicircle and G is the point of the semicircle itself. And this is exactly the definition of radius. Therefore, GO is the radius of the semicircle, that is to say it is equal to R, and therefore, for the same reason, OF is also the radius of the semicircle, that is to say it is equal to R. So GO is R and OF is R, and GO times OF is R times R, that is R squared. MC equals to 3 units. CO equals to square root of 2 times R. Therefore, MC plus CO will be equal to 3 plus square root of 2R times OS, that is 3 minus square root of 2R, will be equal to R squared. This expression 3 plus square root of 2R times 3 minus square root of 2R is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. And in our specific expression, A equals to 3 and B equals to square root of 2R. And according to this trigonometric identity, A plus B times A minus B must be equal to A squared minus B squared. That is to say, this expression must be equal to A squared minus B squared. That is to say, A squared is 3 squared because A equals to 3. 3 squared is 9 minus B squared. B squared is square root of 2R squared. Square root of 2R is square root of 2, that is 2, times R squared. So in conclusion, square root of 2R squared is 2R squared, and minus B squared is minus 2R squared. So in conclusion, we found out that this expression equals to 9 minus 2R squared, and it is also equals to R squared. So we added 2R squared to this equation, and we found out that 9 equals to R squared plus 2R squared, that is 3R squared. We divided this equation by 3 and found out that R squared equals to 3. Okay? And we know that, so we know that R squared equals to 3, and the area of the semicircle is equals to the area of the circle over 2. The area of a circle is pi R squared, therefore the area of the semicircle must be equal to pi R squared over 2. So the area of our semicircle will be equal to pi R squared over 2. We have already found out that R squared equals to 3, so we'll substitute R squared by 3. So it is pi times 3 over 2, or 3 pi over 2. So in conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay, we finished with the first method. In the next step, I will present to you how we found out the area of the semicircle according to the second method. Okay? In the second method, we use the things that we have already found out in the first method. Therefore, we have already know that BOCD is a square, CO is the diagonal of the square, and the length of the diagonal of the square CO is equal to square root of 2 times R. And we have already found out that GO is the radius of the semicircle, that is to say it is equal to R, and for the same reason OF, it is also the radius of the semicircle that is equal to R. Then we join point C and F together by a straight line. CF, line segment CF, it is the radius of the quarter circle. Why? Because it starts from the center of the quarter circle. C is the center of the quarter circle, and F is a point on the quarter circle itself. And this is exactly the definition of a radius. Therefore, CF is the radius of the quarter circle, that is to say it is equal to 3 units. For the same reason, CG will be also the radius of the quarter circle, that is to say it equals to 3 units. Again, it starts from the center of the quarter circle, that is to say from point C, and ends at point D, at point G, that is a point on the quarter circle itself. Therefore, CG is the radius of the quarter circle, that is to say it is equal to 3 units. So, triangle GCF is an isosceles triangle because of the fact that it has two sides that are equal to each other. Here, side GC equals to side CF, and both sides are equal to 3 units. They are the radiuses of the quarter circle. So, here, GF is the base of the isosceles triangle GCF, and OC is the median to the base GF. Why OC is the median? Because it bisects the median to two equal parts. It bisects the base GF into two equal parts. That is to say GO equals to OF equals to R. Okay? So I copied the isosceles triangle GCF in a new page. This is the right triangle GCF or CGF. Again, CO is the median to the base FG. Why CO is the median to the base? Because CO bisects the median to the base, bisects the base CG into two equal parts. OG equals to OF equals to R. But according to rule number 4, the median to the base is not only bisects the base into two equal parts, but it is also perpendicular to the base, FG. So according to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So the median CO to the base FG is perpendicular to the base FG. That is to say CO is perpendicular to FG. That is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 4. So we actually have here two right triangles that are actually congruent to each other. They are identical actually. According to side rule, they are congruent to each other. They have a side CO that is a common side. So we have here two right triangles. Actually the median CO divided the isosceles triangle CFG into two right triangles that are identical. They are congruent to each other. So we will find out here. We will implement the Pythagoras theorem on this right triangle. We can do the same thing also in the other right triangle. So I choose by accident this right triangle to implement the Pythagoras theorem on this right triangle COG. So I copied the right triangle COG in this new page, and here we have, according to the Pythagoras theorem, we know that CO it is equals to square root of 2 times R. It is the diagonal of the square. This angle equals to 90 degrees according to rule number 4. We have already found out that OG equals to R, and CG it is the radius of the quarter circle that is equal to 3 units. So by implementing the Pythagoras theorem, we'll find out the value of r, of course. So according to the Pythagoras theorem, in the right triangle COG, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CG square equals to CO square plus OG square. CG is 3, so CG square is 3 squared, that is 9, and it is equal to CO square. CO equals to square root of 2r, therefore CO square will be equal to 2r square plus OG square. OG is r, so OG square is r square. So in conclusion, we found out that 9 equals to 2r square plus r square. 2r square plus r square is 3r square. So we found out that 9 equals to 3r square. We divided this equation by 3 and found out that r square equals to 3. And the area of the semicircle, it is pi r square over 2. R square equals to 3, so we can substitute r square by 3. In conclusion, the area of the semicircle will be equal to pi times 3 over 2, or to 3 pi over 2 square units, or in terms of numbers, it is equal to 3.71 square units. Okay? So we actually finished with question number 1. And in the next step, I will present to you the second question, how we solve the second question in 2 different methods. We have here the right triangle ABC. Angle ABC equals to 90 degrees. Side BC of the right triangle ABC equals to 6 units. Line segment DF equals to 2 units, and line segment DF is perpendicular to the hypotenuse AC. That is to say, this angle equals to 90 degrees, and this angle is also equals to 90 degrees. And we also know that AE equals to EC, and this angle is angle theta. This is the angle that we are looking for. Angle BAC equals to angle theta, and we want to find out the size of this angle, angle theta. So in order to find out the size of angle theta, we did the construction. From point E, we drew perpendicular on BC. So this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to our construction. And we define the touching point of the perpendicular from point E and BC as F. And then we defined this angle as angle alpha, and because of the fact that in the right triangle ABC, this angle equals to 90 degrees, this angle equals to theta, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. Therefore, we can write down the equation that alpha equals to 90 degrees minus theta, because according to our definition, it equals to alpha, and we just right now found that this angle must be equal to 90 degrees minus theta. Therefore, we can derive from it that alpha equals to 90 degrees minus theta. So in the next step, so if this angle equals to alpha, this angle must be equal to 90 degrees minus alpha. In the right triangle APC, the sum of the angles must be equal to 180 degrees. So this angle, if this angle equals to alpha, this angle must be equal to 90 degrees minus alpha. But here we already found out that alpha equals to 90 degrees minus theta. Here, if we add to this equation theta and we will subtract alpha, we will get that theta equals to 90 degrees minus alpha. So if this angle equals to 90 degrees minus alpha, it means that it is equal to theta. Okay, 90 degrees minus alpha equals to theta. And then we found out the size of this angle, angle DEF. The size of this angle, angle DEF. The size of angle DEF will be equal to angle DEC minus angle FEC. Angle DEC minus angle FEC will be equal to angle DEF, this angle. I repeat again, angle DFE equals to the big angle DEC minus angle FEC. So the missing angle DEF will be equal to the big angle DEC, that is equal to 90 degrees according to what is given us in the question. So we can substitute angle DEC by 90 degrees minus angle FEC. We already found out that angle FEC equals to 90 degrees minus alpha. So we can substitute angle FEC by 90 degrees minus alpha. We did it here, and we got that angle DFE equals to 90 degrees minus alpha. We opened the brackets here, and we found out that angle DFE equals to 90 degrees minus 90 degrees, that is 0. Minus and minus is plus. So in conclusion, we found out that angle DFE, the missing angle here, it is equal to alpha. So in the right triangle EFD, this angle equals to alpha. This angle equals to 90 degrees. So in order to complete the sum of the angles in this right triangle to 180 degrees, this angle must be equal to 90 degrees minus alpha. But because of the fact that 90 degrees minus alpha equals to theta, we can substitute this angle that is equal to 90 degrees minus alpha by theta. So we did it, and we find this angle as theta. Okay, in the next step we defined side DF as x, side FE as y. We defined AE as A, and because of the fact that AE equals to EC, if AE equals to A, then EC must be also equal to A because of the fact that they are equal to each other. In the next step, we proved that the right triangle ABC is similar to the right small triangle FEC. So why those two right triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to theta. Those two angles, they are also equal to each other, they are both equal to 90 degrees. And this angle alpha, is a common angle that belongs to both triangles. So we actually proved that all the angles of triangle ABC can go into all the angles of triangle EFC. Therefore, we can derive that from that triangle ABC is similar to triangle FEC according to angle similarity rule. And from the fact that triangle ABC is similar to triangle FEC, the small right triangle FEC, we will derive that AB over AC in triangle ABC will be equal to EF over AC in triangle FEC. Okay, I'll repeat again. We will derive that AB over AC equals to EF over AC. So AB over AC. AC equals to A plus A, that is to say AC equals to 2A, so we can substitute AC by 2A. EF equals to Y according to our definition, and EC is also equals to A according to our definition. So in conclusion, found out that AB over 2A equals to Y over A. We have A in both sides of the equation, so A will get cancelled, and we left only with AB over 2, that is equal to Y. We multiplied this equation by 2, and we got that AB equals to 2Y. According to equation number 1, AB equals to 2Y, so we can substitute, we can write down here that AB equals to 2Y. In the next step, we proved that the right big triangle ABC is similar to the right small triangle, this triangle EDF. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to theta. Those two angles are also equal to each other, they are both equal to alpha. And those two angles are both equal to each other, they are both equal to 90 degrees. So we can write down that triangle ABC is similar to triangle DEF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that AB over BC equals to DF over EF. Okay? We will derive that AB over BC equals to DF over FE, or EF, it is the same. So AB equals to 2Y, so we substitute AB by 2Y. BC equals to 6, according to what is given us in the question, so we substitute BC by 6, we substitute BC by 6. DF equals to X according to our definition, and FE equals to Y according to our definition. So in conclusion, found out that according to equation number 2, 2y over 6 equals to x over y. Here we divided both the numerator and the denominator by 2, 2y over 2 is y, and 6 over 2 is 3. So in conclusion, we found out that according to equation number 2, y over 3 equals to x over y. Because multiplied this equation number 2, and we found out that y squared equals to 3x. Okay, y squared equals to 3x according to equation number 2, but in the right triangle EFD, if we implement the Pythagoras theorem, we will get that x squared plus y squared equals to 2 squared. It is very easy to see it from the drawing, that x squared plus y squared equals to 2 squared in the right triangle EFD. So according to the Pythagoras theorem, in the right triangle EFD, x squared plus y squared equals to 2 squared, that is 4. So we can substitute y squared in this equation number 3 by 3x from equation number 2, because y squared equals to 3x. We did it and we got that according to equation number 3, x squared and plus y squared is 3x, equals to 4. We subtracted 4 from this equation, and we got the quadratic equation that x squared plus 3x minus 4 equals to 0. This is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, a equals to 1, b equals to 3, and c equals to minus 4. So we will put the data inside the formula for x, and we will find out the value of the values of x. So here in our specific quadratic equation, x equals to minus b, b is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 9, minus 4 times a is 1, and c is minus 4. So it is minus 4 times minus 4 over 2a. A is 1, so 2 times 1 is 2. So in conclusion, we found out that x equals to minus 3 plus minus. Here, minus 4 times minus 4 is plus 16, and 16 plus 9 is 25. So inside the root, we left only with 25. So we got that x equals to minus 3 plus minus square root of 25 over 2. The square root of 25 is 5. So in conclusion, we found out that x equals to minus 3 plus minus 5 over 2. So here we will have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. But because of the fact that x is the length of side df of the right triangle in df, x must be a positive number. So if x is a length, therefore it must be a positive number. It can never be equal to minus 4, that is a negative number. So we cancel this solution, and we left only with the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So in conclusion, we found out that x2 equals to 1. So I copied the right triangle EDF in the new page, and we found out the cosine theta of this right triangle EDF. We know that EF equals to y. We just right now found out that DF that is equal to x equals to 1, and DE it is given us that is equal to 2. So here cosine theta equals to DF over DE. DF equals to x that is equals to 1. DE equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2. So if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So we found out that the value of angle theta, or the size of angle theta, is 60 degrees. We finished with the first method. In the next step, I actually presented to you how to find out. I will present to you how we found out the value of angle theta according to the second method. In the second method, we define this angle as angle alpha. A equals to A according to what we have already did in the first method. EC equals to AE, so if A equals to A, then EC must be also equals to A. And here, in the right triangle ABC, this angle equals to 90 degrees, this angle equals to theta, so this angle must be equal to 90 degrees minus theta. So this angle also equals to alpha, and it is also equals to 90 degrees minus theta. Therefore, we can derive from it that alpha equals to 90 degrees minus theta. Then I copied the right triangle, triangle ABC in a new page, and we analyzed the right triangle, triangle ABC. This is the right triangle, triangle ABC that I copied in the new page. We know that BC equals to 6 units. It is given as the question. Here, the hypotenuse AC equals to A plus A according to our definition. A plus A is 2A, and this angle equals to alpha according to our definition. So in this right triangle, we know that cosine alpha equals to BC over AC. Cosine alpha equals to BC over AC. BC is 6, AC is 2A. So in conclusion, we found out that cosine alpha equals to 6 over 2A. We divided both the numerator and the denominator of this side of equation number 1 by 2, and we got that 6 over 2 is 3, and 2A over 2 is A. So in conclusion, we found out that cosine alpha equals to 3 over A. And here we multiplied the equation number 1 by A, and then we divided by cosine alpha, and we got that A equals to 3 over cosine alpha. So according to equation number 1, A equals to 3 over cosine alpha. Then we focused on the right triangle, triangle DEC. I copied the right triangle DEC, and we analyzed the right triangle, triangle DEC. In the right triangle, triangle DEC, we know that AC equals to A according to our definition, D equals to 2 according to what is given as the question, and alpha, this again equals to alpha according to our definition. So in this right triangle, triangle DEC, we know that tangent alpha will be equal to DE over AC. According to equation number 2, tangent alpha equals to DE over AC. DE equals to 2. EC equals to A. So in conclusion, tangent alpha equals to 2 over A. But we have already found out that according to equation number 2, A equals to 3 over cosine alpha. So we can substitute A in equation number 2 by 3 over cosine alpha from equation number 1. We did it, and we got that according to equation number 2, tangent alpha equals to 2 over A, but A is 3 over cosine alpha. So we got here that tangent alpha equals to 2 times cosine alpha over 3. Tangent alpha is sinus alpha over cosine alpha. So we substitute the tangent alpha by sin alpha over cosine alpha. We got that sin alpha over cosine alpha equals to 2 times cosine alpha over 3. We cross multiply this equation, equation number 2, and we got that 3 times sin alpha equals to 2 times cosine square alpha. And we have the trigonometric identity that states that sin square alpha plus cosine square alpha equals to 1. We subtracted sin square alpha from this equation, and we found out that cosine square alpha equals to 1 minus sin square alpha. Now we can substitute cosine square alpha in equation number 2 by 1 minus sin square alpha. According to this trigonometric identity, they are equal to each other, so we'll substitute cosine square alpha by 1 minus sin square alpha. We did it here, and we got that 3 sin alpha equals to 2 times cosine square alpha, and cosine square alpha equals to this, according to this trigonometric identity, equals to 1 minus sin square alpha. We open the brackets here, and we got that 3 sin alpha equals to 2 times 1 is 2, and 2 times minus sin square alpha equals to minus 2 times sin square alpha. Here we actually found out that 3 sinus alpha equals to 2 minus 2 times sin square alpha. We added 2 sin square alpha to this equation, and found out that the 2 times sin square alpha plus 3 sin alpha equals to 2. We subtracted 2 from this equation, equation number 2, and we got that according to equation number 2, we found out that 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So we have here a quadratic equation. The coefficient A in this quadratic equation is 2, the coefficient B in this quadratic equation is 3, and the coefficient C in this quadratic equation is minus 2. And the variable that we are looking for in this quadratic equation is sinus alpha, therefore x equals to sinus alpha. And the formula to find out the value of sinus alpha, that is x, in this case x equals to sinus alpha, is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So here x equals to sinus alpha, so we write down that sinus alpha equals to minus b equals to 3, so minus b is minus 3, plus minus b squared, b is 3, so b squared is 3 squared, that is 9, minus 4 times a is 2, so it is minus 4 times 2, and c is minus 2. So minus 4 times ac is minus 4 times 2, times minus 2 over 2a. A is 2, so 2 times 2 is 4. So we got that sinus alpha equals to minus 3 plus minus. Minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16. And 16 plus 9 is 25. So inside the root we left only with 25. Then we got that sinus alpha equals to minus 3 plus minus square root of 25 over 2. The square root of 25 is 5, so in conclusion we found out that sinus alpha equals to minus 3 plus minus square root of 5 over 4. So here we have two solutions that are possible for sinus alpha. The first solution for sinus alpha is the sinus alpha equals to minus 3 minus 5, that is minus 8. Minus 8 over 2, minus 8 over 4 is minus 2, so we found out, according to the first solution, that sinus alpha equals to minus 2. But because of the fact that the function sinus can accept values that are ranging from minus 1 to plus 1, and minus 2 exceeds this range, this answer is incorrect answer. In other words, sinus alpha can never be equal to minus 2. So we cancel this solution, and we left only with the solution that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. And we have already found out that alpha equals to 90 degrees minus theta. So we can write down here that alpha equals to 90 degrees minus theta. And because of the fact that alpha equals to 30 degrees, we will substitute alpha by 30 degrees, and we got that 30 degrees equals to 90 degrees minus alpha, 90 degrees minus theta. We add the theta to this equation, and we subtract as 30 degrees, and we got that theta equals to 90 degrees minus 30 degrees. So theta equals to 90 degrees minus 30 degrees, that is 60 degrees. So in conclusion, we found out that according to the second method, theta, the size of angle theta, is also equals to 60 degrees. So in both methods, we found out that the size of angle theta, this angle, is equal to 60 degrees. Okay, thank you very much.